Going to tell us about the GREAT08 survey.
Thank you.
Or challenge.
Challenge, that's all right. Okay, great. I realise, having called this challenge GREAT08, that I use the word great an awful lot, so to excuse me. Okay, it's not intentional. Okay, so I thought I'd use this opportunity to discuss what we could do within the lensing community to bring in other people from outside the lensing community to do a lot of our work for us. So as Gary described, a lot of things which, we've got enough to do. Okay, we're not short of things to do within the lensing community. And I think the lensing community is quite small relative to, say, the CMB community. And yet we've just heard that we've actually got a lot more problems to solve maybe than the CMB community has. So you can debate that with me later maybe. So how can we get other people drawn in to do some of the work for us? So the things that I can think of are this shear measurement problem, and that's what I'm going to focus on for most of the talk. But then maybe there are other areas in which we could specify what we need very accurately and in a way that can be understood by people who are not familiar with all of the lensing details. So basically where I've got a question mark like this, I'm hoping to edit the thing and fill in all your comments. This is more of a sort of trying to sort of provoke discussion on what we might do. Okay, so this is just one of the plots from the Dark Energy Task Force, where you can see the weak lensing has great potential, a very high top to this error bar, but also a lot of uncertainty on how well we can do weak lensing to measure, say, dark energy. And the point is that we want to reduce the size of this uncertainty and hopefully end up somewhere near the top of this error bar with huge statistical power and get rid of lots of systematics. And so Gary mentioned a number of these this morning, and maybe this is a sort of another list which I think we're in fair agreement on of the main problems. So shear measurement, so measuring the shapes of galaxies from images, photometric redshifts, intrinsic alignments, and the accuracy of the predictions of the lensing signal. So I think these are the main things, and I suppose you could talk about these first two as being measurement problems, maybe the second two as being astrophysics problems, and the last two being maybe theoretical prediction problems. And I think the ones that we really have to worry about are astrophysical problems, because these effectively, they're potentially theoretical problems. Like, if we could run a simulation which had the full astrophysics, supernovae, everything in, then we could do a huge amount to predict galaxy colours and galaxy photometric redshift predictions and intrinsic alignment predictions. We could solve all of these if we could do a simulation with enough astrophysics in. But the assumption in drawing this ellipse here is that there are going to be some problems that we're not going to be feasibly able to simulate properly. For example, galaxy spectra with enough accuracy to trust them. So we're trying, though, to sort of push anything astrophysical problems into measurement problems or solvable theoretical problems. And so, for example, for this photometric redshifts, if we can get lots of spectra, then we've turned it into a measurement problem instead of an astrophysics problem. So shear measurement, I'm going to try and convince you, is a pure statistics problem and actually doesn't require any knowledge of astronomy. So I want to try this out on you. So we've got a logo and we've got a name, and what it stands for is slightly not the best acronym ever, but it's a nice one when you finished it at least. Gravitational Lensing Accuracy Testing 2008, which is this GREAT08. It's a fantastic logo which Richard Massey devised, and the name was thought up by Tom Kitching. And so basically this is a challenge to computer scientists from the lensing community. It's been accepted by a large European computer science network as one of their challenges, the Pascal network. And so that gives us a window onto some computer scientists. But I think actually another group of people who are very well placed to try and solve this are people from the CMB community, lots of areas within astronomy which are very statistical, and you'd probably have more sort of confidence to address this problem. Okay, so just to sum up, what is this shear measurement problem? When I say that, I mean that we've got to go from images of galaxies and try and work out the shear that the universe applied to those galaxies from gravitational lensing. And the problem is, so we're basically trying to measure shears, and then we always go and do statistics and try to get cosmology. But we're just focusing in for now on this box here where we're trying to measure shears from images. So just this is the way we're describing it, and I want to sort of run this description by you to try and convince you that this is a statistics problem. Okay, so this is a description that you can go into your computer science departments and use. The slides are all on the web, and basically we're just trying to measure this shear. Okay, so this galaxy has been sheared to get this galaxy, and although shear has a whole load of, there's quite a learning curve to learn about cosmic shear. For the purpose of this problem, the shear measurement problem, all you need to know is that it's just a matrix distortion. Okay, so we just need to know what are these two numbers, G1 and G2. The amount of squashing in the XY direction and the amount of squashing along the diagonal directions. And in this picture here, the shearing is around sort of 0.2. But in reality, with real data, with cosmic shear, then it's going to be about a factor of 10 smaller than that. Okay, so it's going to be a much smaller effect than the actual intrinsic ellipticity of the galaxy itself, and all of this stuff. Okay, so then we're going to convolve it with some kernel, and this is due to the atmosphere and telescope, and in reality the kernel size is a similar size to the galaxy size. So that's one of the huge things that makes this a difficult problem. Then, as you know, we pixelize the image, by which we mean summing the light in each square, which some people, there's a whole debate about whether you call that pixelization, but we mean summing the light in each square. Pixels are quite large, and then we're adding noise, and in this challenge we're keeping it as Poisson noise. Okay. And the noise is actually at a higher level than this, such that the uncertainty on the total light is about 5%. So you can see that this is actually all people need to know in order to address this problem. This is the forward problem, which we're summing up in this picture here. So, as you know, there's very small things that we're looking at here, and I'm just going to show you a quick image from. So, the GREAT08 data is all sitting on a hard disk. It's been created now. It's 120 gigs of data, and we're going to analyse it within the lensing, the GREAT08 team, over the next couple of weeks or so, and then when we're happy with it, we'll put it out publicly. This is what one of the images will look like, and if you zoom in on a 40 by 40 area, then you see we've put the galaxies nice and neatly, roughly in the middle of each of these isolated postage stamps. So you can see here the kind of signal to noise that we're talking about with these galaxies. Okay.
What is the signal?
It's 20.
So the challenge doesn't involve actually finding the galaxy?
No, I mean, I think really it came from our experience with STEP, shear testing program, where we simulated images which were still fairly simple, but we realised that actually we wanted to understand where the problems were, and we wanted to isolate the problems. So we wanted to keep this as simple as we could. And at worst, it's too simple, but hopefully this will lead on to future challenges where we can start putting in more of the real problems. We wanted to isolate as much as possible. I mean, your advice on how best to do this is very welcome indeed. And certainly with this Pascal challenge, this Pascal network, there is a history of successful challenges then having future challenges which go on to build on the previous results. Although actually I went to one of their meetings to hear about their other challenges, and it seemed that a lot of these challenges, the subsequent year was actually simpler than the first year. So we're hoping that using our existing experience within STEP, we've learned a lot of those lessons, and we're starting from a good place. But yeah. Well, there's one which is, let's see if I've got object recognition. no, I don't have it here. Okay, I can show you another time. But they've got one which is trying to find objects within images, like trying to find, say, is this a cow or a person or a wine bottle? And they have to like draw boxes around each of the things on the image. So there are image analysis challenges. I think the big difference that we've got is that if you look at any single image, then you can't really see what's going on. Whereas in their problems, they're things that you can solve by eye, if you had to, but you just don't have time to do the sheer number of images that you've got. Whereas here, any one image has got such a small signal to noise that, and the accuracy that we're looking for is so huge. So that's what makes it very different. So just to briefly say that there's this team from which GREAT08 sort of arose, which is called STEP, Shear Testing Programme, which started about 4 years ago, and we've had a number of iterations of different types of galaxy, different types of observing condition. And so we're basically packaging up something which is pretty similar to our Step 4 into this GREAT08 challenge. So where are we with measurements of shear? Well, this is a plot from the Step 1, just to give you a brief mention. So these are different methods trying to measure the shear calibration, which Gary mentioned, to of order, hopefully within 10%. And the grey band indicates where we were with observations at the time. And so all of these methods within this observation, statistical error for the observations, were doing reasonably well. And all the methods that had been used on existing data were within this band. Our goal at the time was to say, are shear measurement methods good enough for existing data? So that limited the number of simulations that we did. But now we're trying to answer a different question. We're trying to say, in 10 years' time, when we have these fantastic data sets, are we going to be able to measure shear to a good enough accuracy? So we're going to need to lie on this line here. We're going to need 0.0003 on this, rather than the sort of range that you can see here. And it's true that there are methods, for example, Mike Jarvis, Gary and Reiko and Hank's method is not far off being good enough. And in fact, with the number of simulations that were used for this, you couldn't actually be sure whether or not you were on this line to sufficient accuracy for the future.
Do you mean that many zeros?
Yes, I do. That's right. So what Gary showed this morning, Gary showed a 0.001, and that was the multiplicative shear calibration requirement. This isn't the additive one, which might be why. So it's different, yeah. So they are consistent.
Vertical.
But
it's the vertical on that scale.
Oh, wait a sec, sorry. Okay, right. Okay, a whole question about how you quantify this. So indeed, okay, so no, yeah, so you're right. So this should be 0.001 in this direction, and then this one here needs to be around about here. Yeah, you're right. I need to change that. And it's in fact the same thing on this slide then. So this is just to sort of show one of the plots from the Step 1 paper, which shows a breakdown of those previous results for one of the methods, I forget which, as a function of magnitude of the galaxy. So you can see that although the average, whoops, where are we? The average is at about 10%, so 0.001, the dashed line. There's quite a variation as a function of magnitude. And obviously if we're going to measure the evolution of dark energy, then we need all of these points to lie on the line, not just the average to lie on the line. Okay. So I think that was the motivation for moving on to trying to do this GREAT08 challenge. So let's see, so just to summarise, so you can read more about it on AstroPH. This paper was out in February on AstroPH, and it's in fact just last week accepted subject to minor revision in Annals of Applied Statistics. And you can also go to this webpage to find out more information. So there's basically going to be 3 sets of data, and the most important one is this main set here, which is where you can win the challenge, basically. So this main set is about 120 gigabytes of images. In total, there's 27 million individual galaxies. And that's required in order to test whether we've measured shear to the accuracy that we're looking for.
These are the postage stamps?
Okay, so what we've decided is that instead of having every single galaxy in a separate FITS file or separate file, they're going to be pasted together into an image of 100 by 100 galaxies. But they're basically something that you just go in there, you cut out your postage stamp, and you use it. Is that what you were asking?
Yeah. So they all have the same PSF?
Right, well, so there's actually 3 PSFs in total in the challenge, but most of them have the same PSF, and there's a couple of others to look at the dependence on PSF. Yeah. And in fact, so one of the things that we've done in this is that we're actually telling people exactly what the PSF is. So there's going to be some very low noise PSF images, and there's also a functional form that you can use. So we wanted to break this down so that it was not a PSF estimation exercise. We just want to see how well you can measure the shears given the PSF. But indeed, that's definitely a candidate for changing in future.
What happens to the form of the galaxy that you meant?
Well, I would have to, yes, I can't give this information away, I'm afraid. So part of the challenge, so part of the problem, I think, and what makes this an interesting problem to me is, and there's some contention about this, so we can debate this. So what we find is that the shear measurement depends on your assumption about the form of the galaxy. So if you think that it's one type and you actually assumed it's a different type, then you'll get a bias. So you may well ask, how can we possibly expect people to do this challenge in that case? So have we given them enough information to solve the challenge if what I've just said is true? So that's one of the reasons why we've got this low noise data set here, which is equivalent to having, say, a deep image of the sky, which we will have. And it's really from this image and the deep images that we have that we'll try and learn about galaxy properties. And so we're not telling people what's gone in, but they can, in principle, learn that information from this. And if they can't, then we're stuffed, because we won't have any more than that in real data.
Is it low noise and small PSF?
No, because we won't have that. Well, it depends if you think this is a space-based, yeah. So if we were trying to do weak lensing using space-based imaging, then we could never have some other imaging which had an even smaller PSF. So that's our justification for this.
The PSF is the same everywhere.
Yes, there's a small number of images for which there's a different PSF, and we make that clear, and we give the PSFs for those as well. Okay. So there'll be a publicly visible, active leaderboard of results. So what we're aiming for here, right, so you submit the shear for each image that you measure, and we calculate a quality factor from this, which is to do with the difference between your measurement and the truth. And we then put your Q value in here, and so typically we think we're around about here for weak lensing methods at the moment, and we need to be here for future surveys in like 10 years' time. So this corresponds to the 0.0003, which it's a combination of additive and multiplicative, in fact, which goes into this. Because if the shear is wrong, the shear is wrong, and it will contribute to this. So goal is to get Q of 1,000. We're at about 100 at the moment. And you can only submit results once a week, so you can't just keep tweaking random numbers until you get it, is the idea. So where are we right now? So this handbook is on the website. You can read all about it, and there's slides that you can download and use to give talks in your computer science departments. We've been producing the simulations and triple checking them. Obviously, we don't want to find that it's impossible to do it because there's a bug in the simulations. And we're currently, as of about tomorrow, the simulations will be released to the GREAT08 team to analyse internally. And the idea is that we're going to put our own results on this leaderboard at the start of the public challenge so that you can see what you've got to beat. The idea is also that we're going to put our codes out on websites that you can download and reproduce our results. And tweak the code. If you want to just change one number in the code and resubmit, then you can do that. Or if you want to come up with a new method, which is obviously the main point of this, then that's also great. But you could start off by just editing someone else's code if that makes it simpler. Okay. So then hopefully in the next month or so, we'll release these simulations publicly. The challenge will run for 6 months, and then we'll have a final report, and all of the input shears will go public, and people can play to their heart's content. Okay, so any questions on maybe that now? How many people showed interest? Okay, so what we've done so far is we've given talks about it and we've put it on, it's cross-listed, the relevant things, and so what we've got is this website, and there's a place on the website you can click to join a Yahoo Group's mailing list if you want to. There's about 30, last time I looked, 30 people signed up to that, and I see what they write when they sign up, and a lot of them have written, "Hi, I'm a computer scientist in this department, I'm interested in it." But yeah, I don't know obviously if all of those would enter, or whether there's people who would enter that haven't signed up and that sort of thing. And somebody started a Facebook group as well, and apparently there's 30 people on that, but who knows what that means. Could just be people who like the word great, you know. So there is interest, and there's I had some email exchanges with some people about some of the rules about it as well.
Do you have some requirement about the errors? Basically, you want to know the statistic of the errors as a project, right?
That's right, yeah. So people are submitting these shear measurements, and then there's also a column for them to submit their uncertainties on the shear measurements. And what we're doing in the competition is that, this statistic here doesn't use those error estimates, but we'll just do a quick check to see if they're miles off with the error estimate, and there'll be a warning, but it's not actually going, the person with the highest Q wins. So if they don't even submit error estimates, that they'll still win. And the reason for that is just because we can get fairly, getting error estimates on the shear is very important, but we don't feel that that's our limiting problem at the moment. I mean, some people's codes do produce these numbers already, and they seem to be roughly right. So where we're really stuck is getting the systematics down on the measurements themselves. I think that's where we are at the moment, basically. Cool. Yeah, that's fine. Okay. So other challenges. Well, there's a photometric redshifts group called PHAT. It's best to type photometric redshift into Google rather than just PHAT. There's various simulations, and they're trying to compare results and codes within this group. I don't know if that's covering everything. I don't know if anybody wants to comment on how that's going. Is there enough?
It's the most fun if you misuse someone else's code, I think is the lesson of the first exercise.
Right, okay, right. So don't run someone else's code without talking to them first or something.
You do seem to get a negative response when you...
What you mean, people don't do it?
Someone evidently misused the zebra code, and so it came out absolutely qualified.
They did really badly on the challenge.
Model for the originators of the zebra code.
Okay.
So a negative result from the code and the coder.
So does this cover, this is looking at photometric redshift accuracy given a training set and given a testing set?
So the one round they've done so far is just, does your code do anything correctly at all? So it wasn't really testing.
Uh-huh.
Here are the true templates, do you get the true measures?
Okay, right. Okay, so you've basically got a perfect training set, essentially. Yeah, okay. No, I think that's certainly from our lessons in STEP, I think you can't start too simple. You might as well start simple, and if it takes no time at all, you haven't lost anything, have you, really? So one question then that are there other parts of the photometric redshift problem that also need to be addressed that are not currently being addressed by PHAT, or that maybe some of them are going to be addressed by PHAT in the future? Should we be... We want these large spectroscopic redshift training sets available. So do we need... I think there's a... Well, I feel that it's not always in our interest, right, to talk about these large spectroscopic redshift training sets, because it makes it sound like 300 million euros or whatever it is in dollars is not enough, you know. We're doing all this, and we also want to get this huge number of spectra as well. It's good to sort of keep it under the carpet a bit, maybe, while you're trying to get loads of money to do the lensing. But actually, realistically, should we be trying to get all these spectra? Maybe we should be trying to get galaxy formation people very excited about measuring galaxy properties and doing a nice complete survey of all the different types of galaxy, and thereby produce this lovely training set for us. I mean, there's a big problem with trying to get people to do calibration sets, right? I mean, this is technically a calibration set for the lensing PhotoZs. Who's going to fund that? I mean, that's so boring. So maybe that's something that we should talk about, or maybe some people should talk about it. Any things on PhotoZs that we should be doing that we're not currently doing?
Does the fact they mention this business of using correlations of galaxies to...
That's a good question. Yeah, I don't know. I imagine that's beyond the
With the shear estimation, I guess it breaks down to a ellipticity estimation. Whereas for photometric ratios, it seems that you can do significantly better if you analyse a big sample of objects at the same time.
Right. That's a good question. So maybe we need to do somebody needs to sort of do a lot more testing of these proposed methods.
Well, it might be that one way of keeping things quiet is to
Not test them.
at the beginning.
Right. Well, I guess we're on camera here, so what can we say? But yeah, I'm sure it'll all be fine. Anything else? Yeah.
So this is sort of futuristic, but with the on previous talks, so actually put in some strange modification of gravity or dark energy.
Mm-hmm.
See if you could get it back out. I received word from several years ago that we should do that because
So we want an end-to-end simulation of lensing observations, and then a big challenge to remove everything.
I guess I wonder this more with the photo sees if you just put photo see errors into a simulation in different ways and analyze them, what do you get back out? Because it seems like a curve that you know a lot more about what the photo see errors would be.
Right. Okay. So if you basically if you assume something that's wrong, if you assume something about the PhotoZ which is actually wrong, and there's a number of outliers, then how much do you bias your results by?
So you take the line catalog or your whole galaxy properties and you assign them a photo set which may include biases like the segmentation of breaks and things like that, and just see what the practical effect is.
I mean, I think in practice that could be done just using the existing Fisher matrix and just you just project out some of the dimensions, and in principle you get the bias out. Have you done that?
Well, I mean, the extent of it that at least I've done is that when I put in a redshift photo the error distribution, it comes from running photos over on a simulated component. I mean,
So that's propagating statistical uncertainties.
At least the distributions are in some sense realistic, although really weird things aren't in this, galaxies that overlap, galaxies that other redshifts.
Right, I guess I'm wondering about is the simulation for photometry, do you think that's...
No, that's empirical.
So there is a paper by Felipe Abdallah, and others, including Connolly and Offalah and Adam Amara, looking at, and they do use simulations, including reddening. So the Connolly simulations include extinction, and they do look at the true PhotoZ error distribution, and they do lensing predictions as well. I'm not sure if they do exactly what you just described there, but they do look at if you assume it's a Gaussian and it wasn't actually a Gaussian, how much do you shift things? But I can't summarise the results more than that without looking at the paper.
Isn't it a data challenge and a DES?
Yes.
Make a realistic
Yes.
Ray trace.
So I think that there's a lot of work going on challenges on all levels within individual collaborations. Like LSST, I think, has very impressive simulations of the effect of the atmosphere on the PSF and that sort of thing. So, and with DES, then there's the simulations, the ray tracing, and the image simulations with a lot of realistic effects in. So I think there's a lot going on within the individual collaborations, but I think we should be making a lot of that more public. For example, I'd love to see, say, the DES end-to-end simulations going out as a public challenge rather than just within the DES team, and similarly with the other collaborations, I think that would be extremely helpful.
We can certainly get the ellipticity simulations out, but at the moment the inputs are kind of naive. I mean, I can't remember if they're actually Gaussians or they're Gauss-Hermite expansions.
Mm-hmm.
Their things are going to ring very well against a bunch of the code. And that's true for DES, the last time I looked.
Yeah, they're
So,
shapelet simulations, yeah.
Which is kind of scary.
It is, yeah. No, so I think that's still very useful. It's definitely, then it's going to take a long time to build up to the perfect simulations. So I think that's still really, really useful. But we shouldn't take a positive result on those to mean that everything's fine. We should keep going and improving those models. Yeah, that's a good point. Great. Okay. Let's see. So simulations as well, I guess I should not go on forever, but we need to have high resolution simulations, baryons, etc. We'll hear more about this today. Simulations as a function of different parameters, modified gravity, we heard a bit about, as a function of cosmology. Lloyd will talk about that. We want to have analytic equations probably, which will help us interpolate between simulations, many realizations to get all the covariances between L's and between 3-point and 2-point and 3-point in itself, and peak statistics and all those covariances. So there's quite a lot to do on simulations. So how clear is it that the simulations community knows what we need and is working on it? Are people on the case already, or should we be specifying more clearly what we need from lensing? I think the simulations community, they're simulating things at higher and higher resolution, say with no baryons in, but then should they actually be diverting their efforts to doing more stuff with baryons in, which will be more useful to us, or how can we influence this basically to our advantage? That's, hopefully we can cover that in other talks. Or and then we've got different requirements depending on what statistic we want to do. Maybe it's best to start off with the power spectra. We want to do, say, 3-point statistics, peak statistics. This is about beyond the obvious, so what about the peak shapes? This is a first result that we got from Sloan, which should be out shortly, where this is actually, correct me if I'm wrong, this is the first map of the dark matter stacked for clusters. So this is stacking clusters and rotating so that the galaxy light is aligned. So this here is the map of the dark matter, and here is probability as a function of the axis ratio for dark matter. So we're getting a detection slightly stronger for the NFW profile for the dark matter. So if anybody can think of a use for this, then I'd like to hear about it. There are papers by Hober, Bodie, Hopkins et al., which predict this depends on cosmology. Whether it's statistically significant enough to be useful, I don't know. If it can be used for modified gravity, then that'd be interesting. Maybe you need to do this in the X-ray as well. But I'd like to hear your thoughts on that.
This is clusters being stacked.
Yes.
Max BCG
It's using the Custer et al. Max BCG catalogue, yeah, to find the clusters. So the Sheldon et al. And the Hansen et al., yeah, that's just the profile, yeah. Yeah, there's no rotate. Yeah. Yes.
So one thing you can do with this is figure out how old the clusters are.
By looking at how elliptical they are.
Yeah.
So is that, would you want to use the dark matter for that, or would you be happy looking at the galaxy distribution?
Probably want the dark matter, I think, on this.
Mm-hmm.
Worried that galaxy distribution might be
So you might categorise the galaxies according to some optical property to do with age, and then see if there's a evolution of this ellipticity with that optical property.
Sorry, I was thinking of something else. I was thinking when the clusters, these are clusters or stuff.
Yeah, that's right. Yeah.
Yeah, so if they're more flat, they're younger.
Right. Yeah.
So that means that, on the pattern, sigma 8,
Yes.
the blockings along there.
Yes. Yeah. Yeah. Yeah.
So related to Duat's test for non-standard gravity using shape of the X-ray isotopes.
Right, so I think if you did this, so we were trying to think, oh, can this constrain any modified gravity? But then we realised that actually, obviously there's papers doing this with galaxy-galaxy lensing. If you stack in the galaxies, then you can use that to constrain modified gravity. When you do it with clusters, because we're not looking at X-rays at the moment, then we couldn't think of any way to say anything about modified gravity because most of the mass is in the X-ray gas, and we're not looking at the ellipticity of that.
Shape here, the shape.
So you'd have to do that for the X-rays as well and compare the two. Yeah, that would be great. Yeah. Cool. Excellent.
About modified gravity here, are you talking about Mond or theories that...
When I said that, I was referring to Mond. Yeah, yeah. I don't know how to constrain anything beyond that with this, but I'd be interested to know. Cool. Okay. And so the question is whether there's enough people on the case, which I've said already. Intrinsic alignments, I think I won't tell you about them because you know about them. But we need simulations in order to predict this intrinsic alignment signal. We can remove it to some extent using the methods, for example, that Gary talked about with modelling it out. And we can use the redshift dependence of the intrinsic alignments to remove it in other ways as well. But at the end of the day, we're going to have to test whether we've sufficiently well removed the intrinsic alignments from whatever method we have. And we also, for modelling it out, for example, will be helped a lot by having some functional form, some known functional form for the intrinsic alignments, which ideally would come from simulations. So it would be great to have more intrinsic alignment simulations as well. But obviously they need to have very high resolution to be able to identify halos and to measure the ellipticity of those halos. So each galaxy subhalo, we need to be able to measure the ellipticity, and we need to be able to measure the angular momentum. So we need enough particles in the halos. And we also need to be able to decide which halo is an early type and which is a late type, potentially, to decide whether to look at the angular momentum or the shape. Or, of course, if we could have formed the disks in the simulations in the first place, we wouldn't need to do that. Hours of fun. And whether you can actually predict the 3-point statistics and use that to help constrain you, or whether you have yet more problems when you add 3-point statistics in is an open question. Great. So again, it's not clear to me that people who are doing the kind of simulations that would be useful for this know enough about what we need in order to do their simulations to the accuracy we require. So I think there's more work to do on explaining what we need. Great. Oh yeah, okay. Well, I won't go on about this. So usually, I don't normally talk about this because I always feel that the organiser might be really annoyed with me for wasting some of the valuable time on mentioning this. But since the organiser, at least one of the organisers is one of the instigators of this. In fact, we sat in a cafe, 4 years ago here in Toronto, and said, oh, you know, on Amazon it's really handy where you read the reviews of the products. Well, it'd be really handy if there was something like that for cosmology or astronomy papers, which is where this began. But there's quite a bit of CMB stuff on there, but I think I just want to emphasise that it's open to everybody, and sometimes it's useful if you've got a question, if you ask it on here, the answer's then available to everyone else to see rather than just an email exchange. So I think that's a great, very useful thing. I think it's very helpful. Okay, so shear measurement, I hope I've convinced you, is a pure statistics problem which can be addressed by people who don't know any astronomy at all. Please advertise it to your colleagues in computer science departments. Yeah, good luck with PHAT, and and maybe we need some other challenges as well. Thank you.
For questions? Any?
Probably said enough already.
No, we haven't had enough questions in the
Yeah,
talk. Okay, so
fine.
we can just move on. So Alan Evans is going to tell us more about shape measurements.